Okay, this is 3.2, exponential and logistic modeling. So we're going to do some application today, basically. So we do the same stuff we did yesterday, only with basically some real-world type problems, hopefully. Okay, so you know, one thing to understand is that when we're multiplying by r each time, this rate is really 1 plus r. So that's going to be important, and we'll talk about that as we do the homework problems as well. But our growth factor is actually 1 plus r. So when we talk about the percent increase or the percent decrease, that's when we're going to actually find r. So here would be our formula then. This would be, you know, like y equals a b to the x, where this is a, this is b, and this is the exponent. So it's the same formula, only we are using, you know, some different variables here, basically. But we're going to find that r a lot today, and we're going to use that to answer a lot of questions. So here's an example then. We have a population model like this, and we want to tell its exponential growth or decay. That's when we look at this right here, because this is a, b to the t, for example. So our growth factor is 1.021. So basically that 1.021 is really 1 plus r. So we always subtract 1 from it to get r, which is 0.021. Move the decimal place over, and that means that this is really a 2.1% increase. And it kind of makes sense as you start writing it out. Think about it. You know, we start with 786,543. And after the first year, we multiply by 1 plus 0.021. So that 1 represents the initial amount, and that 0.021 is a 2.1% increase of the original amount. So it makes sense, you know, that you would do that. So then when you square it, you're multiplying it 2 times, basically. So it's the same thing. Now you're going to take this previous amount, which was 2.1% bigger, and you're going to multiply it again to make it 2.1% bigger. So each time you're gaining 2.1% per increment of time, whatever unit we use for t, which in this case would probably be years. Okay. So here's a typical example you'll see on the Weber homework. All right, so we're going to use y equals ab to the x still, right? That's our typical standard form for an exponential equation. We start with 200 bacteria, and these double every hour. So our growth rate's 2, and our exponent, I'm going to use t to represent the number of hours. So here is the, you know, the function in terms of t for our exponent, whatever you want to use here. And this will be the number of bacteria. So maybe I want to use n in terms of t. So the number of bacteria depending on the number of hours. So the question is, when will the bacteria reach 350,000? I'd plug in 350,000 here, and I'd solve for t. So I divide both sides by 200. 2 of these zeros are going to cancel. 3,500 divided by 2. Equals 2 to the t, so I would change this into log base 2 of 3,500 over 2 equals t. That's how you go from exponential form to log form. The base always goes here. The exponent is always what a log is, because a log is an exponent, as you recall. So what's left is the argument, which goes here. So there's the base, there's the exponent, and there's the argument. Okay, so that's important to go from exponential form to log form today to solve these problems. We would just type this into our calculator from there. In our calculator, we would do alpha window, which is log base, which is 5. So it would be log base 2 of 3,500 over 2. And we can enter, and that gives us, after about 10.77 hours, so in the 10th hour or after 11 hours, the population would reach 350,000. Okay, so we can do other types of problems where we give it some data, you know, for population in the year, starting with 1890. We'll call that year 0. And then they want us to then use this to get an exponential equation that models that population growth, and then predict when you know, we reach the year 2000, what would the population be? So when we reach the year 2000, what will that population be? Well, we need to get an equation, so we do that with our calculator. We go to Stat, we go to Edit, and we type all this in. So we're going to clear these lists. You're going to enter in 0 through 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 through 9. Ooh, 7, 8, 9. Okay. And then we're going to do the same thing here. We're going to clear this list, and we're going to enter in all the y values for this, which are right here. So I'll enter those in real quick. Once I get all these values in, you just go to Stat, and you go to Calculate, and you scroll down to Exponential Regression, which is 0 or 10. So I'm going to hit 0 for exponential regression. I wanted to use L1 and L2, and that gives me a regression equation of this. Now, what's actually handy is if I go to Stat Calculate and I hit 0, and then I store this regression equation, new software allows you to do this, and I hit vars y variable y1, function y1, it now stores this in my y1 in my calculator, which is kind of nice because then when it wants me to predict for the year 2000, that'd be 110 years after. And in fact, I need to relook at this a second because I was going by tens here. So really, I guess I could do this if I call each of these increments 1, keep in mind that 1 is really 10 years. So if that's the case, from 1890 to 2000, that would be there'd be 11 of these increments after. So I got to make sure that when I graph this, I'm looking for the 11th data point down here because this is the 10th would be 1990, 11 would be 2000. So I need to plug in 11 into my model. The best way to do that, in my opinion, is to do this and look at a quick graph of this data and then plug in 11. And make sure your window goes out far enough because otherwise it's hard to get that point by Stat Calculate. So I'm going to go to second window, just window, and I want my X max to go out past 11, so I'll do 12. I'll graph that real quick. Now my Y value happened to be good in my window. I already had it set to 500, which is actually kind of nice for this one. But when you get this, you can go second calculate value, and then plug in 11. And that's the best way, easiest way to just plug it in and get that value, which in this case is looks at 308.38. So 308.38, and that's in millions of people. So we have to move the decimal place over 6 to get the actual value in millions of people. Okay, one more problem then. High school starts off with 1,500 students. 5 students start a rumor which spreads logistically like this. Miles the number of students who have heard the rumor. By the end of T days, where T equals 0, is the day the rumor begins to spread. How many students have heard the rumor by the end of day 0? We would enter in a 1 right here for this T. So we get 1,500 over 1 plus 29 e to the negative 0.9. This is just something you'd have to evaluate in your calculator, starting with the bottom first, obviously. And you about 117.3 students, so about 117 students. And then how long does it take for 1,000 students to hear the rumor? It's a little harder. We got to set this equal to 1,000, where we keep this a variable t right here. We have to solve for this variable t. We would cross multiply first. So I'm just going to switch these two quantities because you can go ahead and switch these. You get 1 plus 29e to the negative 0.9t equals 1,500 divided by 1,000. Move the decimal place over 3, that'd just be 1.5. And then I subtract 1 from that. So that gives me 29e to the negative 0.9t equals 0.5. Divide both sides by 29. And then take the natural log of both sides, or put it in the log form, either way. Gives you the same thing. It gives you negative 0.9t equals natural log of 0.5 over 29, and then divide both sides by negative, and you get t equals natural log of 0.5 over 29 divided by negative 0.9, which gives you, so this will be about 4.5 hours. You go ahead and solve that in your calculator. All right, we'll try some homework, and hopefully we can get some good practice with this.